General relativity predicts a number of consequences, and while science fiction writers are quick to use these in their stories, a number of these consequences are worth exploring even in physics. Two of these consequences are particularly interesting to both sci-fi writers and physicists because they deal with the possibility of time travel. The first of these is gravitational time dilation. It is a form of time dilation predicted by general relativity, the way special relativity predicts time dilation due to relative velocities. But gravitational time dilation has nothing to do with moving. Instead, it predicts that time passes slower for observers closer to a gravitational mass. So that means that time passes slower down on the Earth compared to the time on top of a mountain. This concept is especially useful to you, me, and most people on this planet. Why, you may ask? Well, our GPS uses signals that come from satellites. These satellites are moving high above the Earth. That means that if we want to synchronize the GPS time with the time down on Earth, the GPS time has to be adjusted to account for the time dilations predicted by both special and general relativity. That is, the GPS clock needs to take into account the fact that it is moving, that it is further from gravitational mass. If GPS time was not adjusted, Google Maps and all other navigation applications would wrongly calculate your position, and it would appear to them that you are several kilometers away from where you actually are. So now, how does this affect time travel? Well, using the ideas of time dilation, if we could somehow get close to a much heavier body, we could age perhaps a few hours, while the Earth and its inhabitants would age many years. So we could possibly return 50 years later, having aged only 2 hours. But that heavy body would have to be a lot bigger than our Sun. If we wanted to travel a substantial amount into the future, we would have to orbit a black hole for a few hours. Unfortunately, we do not have the technology capable for doing this yet. So now you know how we could theoretically travel into the future. But what about the past? Well, Einstein's equations gives us a way of doing that too. But it is unlikely to be any easier to travel into the past than it is to travel into the future. Einstein's equations predict what we call wormholes, shortcuts through space-time. They're like tunnels linking a particular point in space-time to another such point. Depending on the times connected by these wormholes, you could move into the past or the future by traversing one. A wormhole could, for example, link a point in Pisa 2015 to a point in Los Angeles 1776. Unfortunately, the wormholes that exist in nature would be extremely difficult to traverse. It is predicted that most existing wormholes would collapse onto themselves. And even if they can avoid collapsing onto themselves, there are very low chances that the 2 points in space-time connect the 2 points we wanted to connect. For example, instead of taking us to London in 1687, a wormhole might take us to a supermassive black hole in the middle of the Andromeda galaxy 10 million years ago. It is still possible for technologically advanced civilization to create wormholes, but even those wormholes might be too narrow for humans to pass through them, and perhaps nothing but light can pass through a wormhole. And so, we have a long time to wait before time travel through wormholes becomes a reality. Until then, you can contemplate the fact that there are tunnels that cut through space-time. Or, you could pity the people who time traveled back into our time, and then realize that we don't have the technology to take them back to their time.